So can you see my screen now? Can you see my screen?
Yes, sir.
Yes, sir.
Okay, okay, thank you. So let me recall what we did in the last class. So in the last lecture, we introduced norms on a vector space, and we are considering only finite dimension vector space here because we want to study matrices. So we define norm. Norm is a function from a vector space to R that satisfies certain properties, the four properties: non-negativity, positivity, homogeneity, and the triangle inequality. And then we saw first we saw some examples of norms on Fn, that like Euclidean spaces, Rn or Cn. And then we saw that using these norms, we can actually define new norms on any given finite dimension vector space over F. So, and then we saw some other way to define many more or many new norms on a vector on a finite dimension vector space using some non-norms on that vector space. Then we saw some first we saw some algebraic properties of norms, like addition of two norms is again a norm, maximum of two norms is again a norm. Then we saw also saw some analytical properties. So we already know, I am assuming that you already know from function analysis or from some other course that you know the notion of convergence with respect to some norm, convergence of a sequence of vectors with respect to some norm. So we saw that if we are working in a finite dimension vector space, then we can talk about several or there are several functions that satisfy the properties of a norm, and therefore they become norm. They can behave or they can be taken as a norm. But then we saw that there is a relation between these norms. In fact, we proved that if we take any two norms on a finite dimension vector space, then they are equivalent. So what is the meaning of saying that? They're equivalent in the sense that so if we have like two norms, let's say uh, norm A and norm E. If we have two norms on a finite dimension vector space V, then there exist two constants C1 and C2 satisfying these, such that this relation this relation is true for this relation is true for all vectors x in the vector space V. So what does it mean? It means that roughly we can say that any two norms are almost the same as each other. So that means up to a constant, of course, up to a constant multiple, all the norms are same. So for certain purposes, one norm is like as good as any other. So for example, certain purposes, when I say, for example, when do we say a sequence of vectors is convergent in a vector space with respect to some norm? So, so if suppose we are given a sequence Vn of vectors in a vector space, then this sequence is convergent to a vector, let's say V, with respect to some norm, let's say a norm. Then if this is true, right? Limit of n tends to infinity, norm of v minus vn with respect to a is equal to 0. So now for certain purposes, for example, this kind of thing, if a sequence is convergent with respect to one norm in a finite dimensional vector space, then it is convergent with respect to any other norm also. So therefore, one norm is as good as any other norm on that vector space. However, this is true in theory, but in practice, uh, this result is of limited use because the constant here, these constants are like they are very different from each other. Uh, they can the difference of the C1 and C2 could be very large, especially when the dimension of the vector space is large, and therefore they are very like less practical. They are of very less practical use. Okay, and I have already mentioned in the previous lecture that depending on the problem, depending on the purpose we are using using a norm for, um, certain norms have some advantages, right? Because two norm is continuously differentiable, one norm is used in statistics, infinity norm has some other advantages. So because of that, this result, although we can say that roughly any two norms are almost same, but actually in practice this result is of just some limited use, and depending on the purpose we actually select the norm. So this is what we saw in the last lecture. So we start today's lecture by introducing another way of like say producing norms on a vector space, on a finite dimensional vector space. So so if I produce some norms on Fn, then using this norm I can generate new norms on any given finite dimensional vector space, right? So in the next result, I will introduce dual norm. So what is the meaning of dual norm? How do we define? And we will do it for a vector space, but using for Fn. But using this norm, you can define new norms on any finite dimension vector space. All right. So in the next, we will introduce dual norm. We will define dual norm. All right. So here from here we start today's lecture. So this is like another way of defining norms using some well-known norm on a vector space. So suppose that we have vector space Fn. So let me recall what is the if we have a vector space, what is the dual of V? So what is the meaning of dual? What is the dual space? Can you tell me? What is dual of V? Just the definition. What is the dual space?
Set of all linear functional from Fn to F.
Yes, set of all linear functionals. That is dual space. And if V is of finite dimension, then there is an isomorphism between V to V dash. So every linear functional can be identified by by a unique vector in V. All right, so this information we can use in order to define this dual norm. So suppose that we have a vector space V which is Fn, and suppose that we have some norm on this. So let's say this is some norm on V. Okay. Then using this we define a function, and I'll tell you why this is called dual norm. So we'll define a function. How is this function defined? So this function we denote it by this superscript star. This is a function from V to R, and how it is defined? You can take if you take any vector x in this, then the value of this vector x under this function is nothing but supremum of this, where y is in Fn. You can take norm of y equal to 1. So basically, what is this inner product of x and y? Inner product, when I'm writing inner product, if I don't mention anything, then you assume that it is the standard inner product on Fn. So if it is, let's say, if f is c, then it is just y star x, and when f is r, then it is just y transpose x. Okay. So if I'm not mentioning anything, any particular inner product, then you assume that this is the standard inner product on Fn. All right, so you can uh, first you can check that this function, whatever function I have defined, this function is a well-defined function. So if I take any x, then for this quantity exists, this soup exists. Why this is the case? Because this function y star x this is a continuous function of y. For a fixed x, this is a continuous function of y. Okay, and also this is a unit sphere. So maybe you can take unit ball, although it would be equivalent. So you can take, let's say, so this is a unit ball under this norm. So every continuous function on this unit ball. So unit ball is compact in Fn. With respect to this norm, it would be a compact set. And this is a continuous function. So every continuous function on a compact set attains its supremum and infimum. So this supremum exists and it is attained. Okay. So basically you can replace this max by a supremum by a maximum. So instead of sup, I can just write max. Okay. Not only this, you can actually show that this quantity is actually same as max of y is in Fn, where y is a non-zero, and you can it is the same thing. It is a different way of writing, and you can actually check that these two maximum are same. Okay, so these two things are same, so it's the same thing. In fact, you can, I'll give you an exercise where you can check that instead of this set, I can just take the boundary of this unit ball. That means only the unit sphere I can take, or I can also replace this function here with some other thing, and still it remains same. So I'll give you that as an exercise, but here you can either you define it using this set where you consider only the vectors of length of norm less than equal to 1, or you consider any non-zero vector with this function. Okay, these two maximum are same. Why they are same? So let us check why they are same. So let me call this as the first one, and this is as second. So I'll show that 1 is 2. Okay. So this function is well defined, as I already mentioned, and these two things are also same. In fact, there are other ways to write this also that you can verify. But why these two things are same? First, let us check that. So why these two things are same? So let us see here. So why these two things are same? I will write here a brief justification. So let us look at the first one. So what is so maybe let's say we start with the second one. Okay, anyway, so let us suppose that y is any non-zero number such that for a fixed x, I am checking this, for a fixed x, I am checking. So y is not equal to 0, and let's say norm of y is less than equal to 1. Okay, then this thing here, this I can do it in this way. Y is non-zero, so I can multiply with length of y or norm of y, and I can also divide with the norm of y here, right? But since norm of y is less than equal to 1, so this quantity is actually less than equal to this, right? And this is true for all y whose length is less than equal to 1. So basically what we have is the following, that for any y not equal to 0 whose length or norm is less than equal to 1, inner product of x with y absolute value is less than equal to this, right? This is true for all y not equal to 0 and norm y is less than equal to 1. But what does it mean? This implies that if you take the maximum over all such vectors, then this implies that 1 is less than equal to. But similarly, you can show 2 is equal to I mean 2 is less than equal to 1. How to show that? So now you take, let's say, so what we have, 2 is actually the following: max of all max of this quantity here, this ratio over all vectors, such that all over all non-zero vectors. But then this quantity, what I can do here, I can write it as so y I can replace by y divided by norm y. So I can write it as y not equal to 0. So what I can do, I can take this inside and I can write it in this way, right? The same thing. But then this is of length 1 or norm 1. So this is actually true. This is equal to the max of all y such that norm y is less than or norm y is equal to 1, is equal to 1, and then this. But then this is maximum over all vectors whose norm is equal to 1. So definitely this is less than equal to max of all vectors, non-zero vectors whose length is less than equal to 1, right? But then this is equal to, this is the first. So 2, so this implies that 2 is less than equal to 1. In this way, these two max are same. So not only this, I can give you, in fact, you can show the following. So let me give you this as an exercise. So what is the exercise? Exercise is that for any norm, you can show that dual norm is equal to max of, you just have to consider the boundary. That is also fine. Or the same thing I can write as y star x also, right? This also I can write. But then you can prove that this maximum is actually equal to maximum or all y. So this y is non-zero, okay? Y not equal to 0. Real part of y star x. Or you can show that this is also same as max of, just consider y with norm 1. This. Okay, or you can show that this is same as max of y to 0, real part of y star x divided by. So all these maximum are same. You can check that. So this you can take as an exercise. Anyway, so what I was saying here, so that is the following, that for any norm on V, we can define this function. This is a well-defined function. And in fact, this function satisfies all the properties of a norm. So this is actually a norm, and we call this norm as a dual norm of this norm here. Okay, so let me write this again here. So this function here, this is a norm. So you can verify this simply using the four properties of norm. You can verify that this is a norm on Fn. This you can check yourself. And this norm is called as the dual norm of F. Dual norm of the given norm is called the dual norm. Dual norm of this norm. Okay, so for any given norm on a vector on Fn, we can define its dual norm. Okay, we'll see what properties it satisfies, but at least we can say this much. Now the question is why it is called dual norm. That also you can see why this is called a dual norm. So I'll give you some idea why it is called dual norm. So why is the name dual norm for this norm, this function? So why it is so? Because, so let me write why the name dual norm. Is, so the one justification you can give is that this naturally arises from the dual space, from the relation between the vector space V and its dual. So here V is Fn, right? And we can consider its dual space, which is the collection of all linear functionals on Fn. So this is the dual space. Okay. Now we know that, so I'm just recalling one result from your basic linear or the standard linear algebra, that if we have any vector z in Fn, then for this vector z, I can define this functional on Fn as follows. So for any z, you can see that this f subscript z, fz, this is a linear functional. This is a linear functional. And in fact, you can show that if you take any linear functional on this dual space, then it would be of this form f equal to fz for some z. This is because of the Rees representation theorem. So also by Rees representation theorem, we know what we know that if f is in v dash, f is a linear functional on v, then there exists a vector z in v such that this f is equal to fz. So that means every vector, every linear functional in v dash is of this form fz corresponding to a unique z, right? So every linear functional can be identified by a vector, right? So then the question is, how big is this linear functional fz? Okay, so the question now you can ask, okay, this is fine, but now how big is the linear functional fz? If you want to measure, like you are measuring vectors here using the norm, then you can ask the same question: what about the size of this fz? So how big is this linear functional? So how big is the linear functional? Linear functional with respect to relative to some vector, right? So what is this fzx? You know, fzx is actually uh, z star x, right? This is how it is defined. So now the question is, what is the length? What is the length of this fzx relative to x? Okay, so therefore you can actually talk about this, because for fz, this fz is defined by unique z. So you can just give it a name and you can talk about how big it can be by taking this relative to length of x. Okay? And this is why it is called a dual norm, because it is naturally arising from this. All right, so now again let's make some observation here. So this is just for the name. Now let us make an observation. So now one thing is clear, that using this norm, using the dual norm, you can define other norms. So for example, if you want to define some or few more norms on Fn, then what you can do, you just take a norm, any norm, and then you define its dual norm, and this is again a norm on that. So it gives another way to define new norms on Fn. Okay. So now one thing is clear. So by definition of norm, by definition of dual norm, what we know, so if for any z, its dual norm is defined in this way, right? The max of y not equal to 0, and you just look at this. This is by definition. So what we can say from here, we can say, so you tell me whether this is correct, whatever I'm writing, that makes sense or not by definition. So this quantity is always less than equal to dual norm of z. So this inequality is true for all y. Is this true? So for a fixed z, this inequality here is always true. So can you see it?
Yes, sir.
And why is that? Why is that?
Sir, because norm is maximum, and if we define for general inner mod of inner product of zy, then it should be less than or equals to that maximum value.
Right. Because this norm is the maximum, is the supremum over all such vectors, and therefore this. Not only this, what you can say that for a given z, this is the smallest constant that satisfy this. So what I'm saying is the following, that not only this, you can say the following also, that so moreover, for uh, for given z in Fn, you can say that this dual norm of z is the smallest constant, c, such that this is the smallest constant c such that this inequality holds for all y in Fn. Can you see this also? Can you tell me why this should be smallest, or this is the smallest constant that satisfy this inequality? So for any given z, dual norm of z is the smallest constant c such that this inequality is true. This is the smallest constant. So we cannot find any other constant smaller than this that satisfy this inequality for all y. So why this is the smallest? So can you tell me why this is the smallest? Anyone? So why this is smallest? Because you can see here, we have already seen that this maximum is actually supremum, and supremum is the least upper bound. So if you want to see this, you know that supremum is the least upper bound. So if you just look at this quantity here, this is less than equal to c for all y. That means c is an upper bound. And by definition, we know that this length of, or sorry, dual norm of z, this is the least upper bound for such inequality to be held, right? And therefore, this is the smallest constant that satisfy this. Anyway, so let us look at some examples of dual norm. So let's take some examples. So we consider some well-known examples. So let us take so let x and y are two vectors in, let's say, Cn. Okay. And assume that the components of x are x1 to xn, and components of y are y1 to yn. Okay. Then you can check that if you take the inner product of x and y, then what it is just y star x with respect to the standard inner product. So what it would be? It would be summation yi bar xi I equal to 1 to n. Then this you can use the triangle inequality for the modulus. So this would be less than equal to I equal to 1 to n mod yi xi, right? But then this quantity you can write as less than equal to, you can take the maximum over all such yi. So you can take max. So what I'm doing is the following, that you here this quantity is less than equal to this thing. Each yi I am replacing by the maximum over all such yi. So max of I nth yi. So each yi I have replaced by this. So it is again an less than equal to, and then mod xi. Now this is a fixed quantity here. This is a fixed quantity. So I can take this out. So what it would be? It would be max of mod yi and summation I equal to 1 to n mod xi. Right? But then what is this? Can you tell me what is the first quantity here? In terms of norm, can you tell me what is this?
Sup norm of y.
Yeah, this is L infinity norm or sup norm. And what about the second one? Second sum here?
L1 norm.
It's the L1 norm of x. So let us call this. So what we have seen here is that for any two vectors x and y, their inner product, the absolute of inner product, is always less than equal to this one. Okay, this is true. So let us call this star. Okay. Now, what you can say from here? So just recall the observation we just made here. Now, from this observation, what can you say from this inequality? What you can say from this inequality? So what can you say about the dual of one norm here from this inequality? So if you look at here, yeah, can you repeat again?
So like dual of one
Dual.
norm is sup norm.
Is sup norm, or can you say from here that this is sup norm? The dual of one norm is sup norm. Can you say from here? From here you can say that the dual of one norm is actually less than equal to sup norm. So what you can say from here? From here you can say that for a fixed y in this, the dual norm of y, or dual of one norm, is less than equal to dual of infinity. This is what you can say, or not dual, but infinity norm of y. So because we know from here that this dual norm is the smallest constant that satisfies such an inequality, and from there you can say that this is less than equal to this.
Yes.
Right? But yes. Do you have any doubt here?
No, sir.
Now this is less than equal to this, but in fact you can show that this is equality. So how we can show, what would be the way to show that this is actually an equality? How can we show that? Yeah, guys, you have to tell me. I'm not going to
Achieve that
do anything
conversion.
further. Yeah. Yes. Can you please come again?
So like this basically constant is equal to like the infinity norm at some y. So
So basically what you have to show, so if you go, yeah, if you just look at the definition again, so what we are trying to do here, so what we are trying to do, we know that if I take any vector x, or let's say y, then its dual norm is this one, supremum or maximum, whatever you write, y not equal to 0, and sorry, x, and then this. But what is the meaning of this? That means that this dual norm of y is the least upper bound. So that means this is, so to show that something is a supremum of a set. So this is a set, right? The right hand side is a set. Now you have to show that the supremum is something, because you are trying to show that this supremum is equal to some constant c. Okay, so that means you are trying to find dual norm of y. So what you have to do, you have to first show that it is an upper bound, and then you have to show that that upper bound is actually the least upper bound, in order to say that this is a maximum. So that means you have to show that this upper bound is attained. So this is an upper bound and this upper bound is attained. So here we have found an upper bound, but we have to show that if you want to show that this is equal to this, that means we have to find a vector for which this expression is, so, or this is actually an equality. Okay, so what we have to do here, so if you choose, let's say x equal to ei, where I is such that infinity norm of y is mod of yi. Okay, if we do this, then what would be this one? This is just, if you just calculate this one here, by definition this is just infinity norm of y. So what does it mean? This implies that in this star equation star we have equality. So in fact we can say that dual of one norm is actually infinity. And using similar argument, exactly is using the same steps, you can show that similarly. You can show that um, if you take the dual norm of dual of infinity norm, it is one norm. Okay? This you can take as an exercise. Same way. First show an upper bound that is clear from this expression here. Now instead of y, you can say the similar thing for x. Okay? And then by choosing an appropriate y, you can show that these two things are same. So for one norm, for L1 norm, dual is infinity norm, and for infinity norm, dual is one norm. This is clear for me. Similarly, we can say something for two norm also. So similarly, you can say that, so what you can say, you know that this is always less than equal to this, right? This is because of Cauchy-Schwarz inequality. So this expression is always true for any two vectors x and y in Cn. So clearly you can say from here that dual of two norm is actually less than equal to two norm itself. But in fact, you can show that this is an equality. That means, or in particular, if you just take this vector, what should be the vector? We should, what we can take here? You can take x as y, and you divide it by its norm. Okay. So this vector you can take, and then if you do this x, y, then this is just two norm of y. So this implies that dual of two norm is actually two norm itself. Okay. So what we have seen so far in this example, we have seen that So from this we can conclude, from this observation or from this example we can make this observation that when p is equal to 1, 2 or infinity, then we have the following, that if I take the dual of dual, so dual norm is again a norm, so we can talk about its dual, so it is like double dual kind of thing, okay? Double dual norm. So we can show that, or we have seen, at least for these examples, we have seen that dual norm of p is actually a dual norm of this p norm when p is 1, 2 or infinity is the p norm itself, right? But this is true for any vector norm on Fn. So we have seen, at least in this example, but you can actually do this. This proof you can find in any standard textbook. So I'm just writing this result. So if you take any norm, vector norm on Fn, then its double dual is the norm itself. Okay, so you can take this as an exercise. Also, you can take one more exercise, and you can show that if p is greater than 1, less than infinity, okay, and q is such that 1 upon p plus 1 upon q is equal to 1, then you can show that dual of p norm is equal to q norm. This follows by using Holder's inequality. This also you can find anywhere, like it is available on internet also. So it is also an exercise for you. So for p norms, at least we can say we know from this so far, we know what would be the dual. And one interesting thing we have noticed here, we have noticed that at least for p norms, you can see for p norms, when p equal to 2, then this is the only case when dual is equal to the norm itself. So dual norm is equal to the norm itself. Only for two norm we have seen that its dual is the norm, right? For other norms they are different. At least for p norms we have seen. For LP norms we have seen this, right? But in fact you can prove this, that this is the only norm. So that means this 2 norm is the only norm on Fn, only vector norm on Fn, for which we have for which the dual norm is the norm itself. This is the only norm. There is no other norm that satisfy this thing. So this one can prove. So proof is not difficult, so I'll prove this also. Let me write the statement first. So what it says that if we have a, so if suppose we are working in Fn, and this is a vector norm, any vector norm on V, okay, and suppose that and let this is the, and let this be the dual norm. It's dual norm. So we have a vector norm, so we can talk about its dual norm also. Suppose that this is the dual norm, and assume that we have a constant c which is greater than 0. Okay, then we can show that norm is equal to c times dual norm. So when I'm writing this dot, means it is true for all x. Okay, you can write it in this way also, for all x in V, if and only if norm is a root 2 times root c times 2 norm. Okay, this you can prove. So in particular, from this result you can say that if this result is true, then you can conclude that when c equal to 1, then norm is equal to its dual when C equal to 1. But then this is true if and only if norm is equal to 2 norm. Okay, so this is the only norm uh, that satisfy this thing for which dual norm is the norm itself. Okay, let us prove this. So I'm proving this just to give you one more way or some idea how to prove results on norms. So like how to show the inequality or how to show that something is equal to a norm or not. So just this is the reason I'm doing this proof here. This will give you some idea how to like prove or solve problems based on this kind of thing when you have to show something is a norm. Okay, so let us prove this. Okay, if you have any doubt at any point, you can ask. So this is if and only if. So we have to prove both ways. So only if is much easier. So only if, let us prove only if direction first. So only if means suppose that a norm is equal to root C times 2 norm. Okay. Now we have to show that this relation is true. That means norm is equal to C times its dual. Okay. So let us see what is the dual. So if I take any vector x, then its dual by definition, what would be the dual? So the dual is by definition max of max over all vectors y with length 1 and of this inner product, right? By definition. So you instead of this I can, so since it is fn, so just to simplify the notation I can just write x star y. This is the inner product of x and y. So this maximum is taken over all vectors with norm 1. This is by definition. Okay. Now this quantity here, what is this? By assumption, by hypothesis, this norm is equal to root C times 2 norm. So I will replace this norm by root C times 2 norm. So what it would be then? It would be norm 2 norm of y is equal to 1 upon root C, and the objective is x star y, right? So far so good. But then you can see here, if I replace y, so it is same as this because I can replace y by y divided by root C by a factor root C. So it is same as this x star when I replace y by y upon root C, and I can just consider norm 1 vector C, right? It's the same, it's the change of variable here. But then again, since 1 upon root C is a constant, so I can take 1 upon root C outside here. Root C is a constant, so I can take 1 upon root C outside. So it would be like max of 2 norm of y equal to 1 and then x star y, right? But then what is right hand side? So what is this quantity? Can you tell me what is this one here? What is this?
Dual of 2 norm.
Dual of 2 norm. So this is dual of 2 norm. So I can write this as this one. But we know that dual of 2 norm, we have already seen in this example here, I mean in the previous example, that dual norm of a vector is the norm itself, right? For 2 norm, dual norm is the norm itself. So this is same as this one, right? But then what is this? Again by assumption 1 upon root C. What is 2 norm? By hypothesis, it is 1 upon root C times norm of x. So 1 upon root C times norm of x, But then what is this? It is 1 upon c times norm of x. So this implies that the norm of x is c times dual norm of x, and this is true for all vectors x. Okay. So this proves the only if direction. Now let us prove the if direction now. So if direction means, let us assume that so conversely assume that norm is equal to c times dual norm. Suppose that this is given for some constant c greater than 0. Okay. Now what is our claim here to show? Our claim is to show that this norm is actually root c times 2 norm. This is what is our claim. Okay, we will show this. Now you can see here. So we will show this by showing both side inequality here. We will show by showing both side inequalities for this expression. So what you can do here, if I take any vector x in V, then what is the 2 norm? What is the 2 norm of this vector? It's a 2 norm square. It is just by definition x star x, right? But then we know that for any, we know, right, x star for any vector x and y, this expression is true, right? This we know for any norm, the expression is true. So I will use this inequality here. So this quantity is always less than equal to dual. Do you agree with this? Now what is this one? The right hand side here. Given is that norm of what is given? That norm is equal to c times dual norm. Okay. So what I can do here, it would be c times dual norm. So in place of dual norm, I will write 1 upon c times the norm itself. So it would be 1 upon c times norm x square. So what we can say from here, we can say that norm of x, 2 norm of x square is less than equal to 1 upon c times norm x square. This is true for all x in V. So from here, we can say that root c times norm 2 norm of x is less than equal to norm x. This is true for all x in V. So this proves one side inequality. So we have to show that these two things are same. So now we will prove the other side inequality. Okay. So let us call this star. So again, let us make some observation that if x is not equal to 0, then what is its dual norm? So what is the dual norm of x? By definition, it is max over all norm 1 vector and the max of this quantity. And also given that dual norm of x, this is given to us that dual norm of x is nothing but 1 upon c times norm of x. So we can write that this is actually this one. Okay. Now here I can write this thing. I can write as follows. This is max y not equal to 0, and I can replace y by y upon y divided by its norm. So these two things are same. These two max are same. This is just I'm taking y, I have divided y by its norm. So you can easily show that these two maximum are same. This is fine. Now what you can do here, since y is non-zero, so you can divide, you can multiply by 2 norm and you can divide by 2 norm of y, because y is non-zero, so we can do that. So what it would be then? It would be max over all non-zero y, and then I can write it as follows: the 2 norm, and then this one would be norm 2 norm of y and divided by norm of y. Right? Now you can use this star here, whatever we have already proved. That from here you can say, what you can say from here, you can say that 2 norm of y, the ratio of 2 norm of y and norm of y is always less than equal to 1 upon root c. From here you can say that this is less than equal to 1 upon root c, because this expression is less than equal to 1 upon root c from star, and then the remaining thing is same. So you can write it as follows: x star y divided by, or you can write it in this way also, x star y divided by 2 norm of y. Right? But then what is this thing? This is 1 upon root c, and this quantity is just 2 norm of uh, uh, dual norm of x, dual norm of dual of 2 norm, sorry, dual of 2 norm here. But then we know that dual of 2 norm is nothing but the norm itself. So from here, what we can say from these two things, what we have is 1 upon c norm of x is less than equal to 1 upon root c 2 norm of x for all non-zero x. So this implies that norm of x is less than equal to root c times 2 norm of x. This is, let's say, double star. So from now, from these two expression, we can say that norm is actually equal to root c times norm, and we are done. So 2 norm, L2 norm is the only vector norm on Fn for which the dual norm is the norm itself. Okay. All right. So we have talked about some algebraic properties of a norm. We have talked about some analytical properties of a norm. Now let us look at some geometrical properties of a vector norm. Okay. So some comments, I'll just give some comments on the geometrical properties of vector norm. So basically, there is a nice way to see a norm geometrically. So one can actually show that if you, or one can actually prove that if you know some information about the unit ball with respect to a norm, then actually you can tell many things about a norm. So basically, you can say that unit ball is a geometric summary of a norm. Why this is true? Because of the following. So let me just briefly mention this. So next time, making some comments, just knowledge. It's not that important, but you should know this also. Some comments on the geometrical properties of a vector norm. Okay. So let me first. So when I say unit ball, what do I mean? So if suppose we have a vector norm, so suppose that we have a vector space, and this is a vector norm on V. Okay. Then what do I mean by a ball? A ball is nothing but a collection of, or ball of radius r around a point x, or around a vector x, is the collection, or maybe we write this. So the ball of radius r around a point x is the following set. It is the collection of all vectors y in V whose distance from x is less than equal to r. Okay, so what is the notation we can use for this? This is a ball, B for ball, with respect to the norm. So norm we can mention here. Center at X and of radius R. So this is the ball with respect to norm, this at center X and of radius R. So this is collection of all vectors Y whose distance from X is less than equal to R. Okay. And if the radius is equal to 1, then it is called uh, and when center is the origin 0 and radius is equal to 1, then it is called unit ball. So what is unit ball? Unit ball is this one. This is the unit ball. Okay. So now you can see that if you can easily why it is called that if you know things about, or you know some properties of a unit ball with respect to some norm, then you can say many things about that norm. Why this is true, or why we say that the unit ball is a geometric summary of a norm? Because if you take any ball, you can take any ball of centered at anywhere in the vector space and of any radius, any positive radius. If you take that ball, then you can always shift that ball to the origin. So what I'm saying is that you can take any ball here anywhere in the plane, and then you can always say that this ball, you can treat this ball as a ball of same radius centered at the origin. Same ball, but you can translate this ball to the center. You can always do that. So if there is a ball anywhere in the plane, in the vector space, you can always translate that ball to the origin. Why this is true? Because of the following thing, you can easily verify that. You can verify that for r greater than 0 and x is any vector in V. You can show that this ball with respect to a norm centered at x and of radius r. What is this ball? This ball is nothing but, you can show that this ball is just this one. This is x plus uh, unit, not unit ball, it's a ball centered at origin and of the same radius. So basically you can see that this ball of any radius r around any point x, this looks same as a ball of the same radius around 0. So it is just translated to that point x. So it is like you have a ball somewhere here on the origin, and if you want to talk about what happens here, you just shift this ball to here. Okay, and since it is for any r, so you can now consider that. So what you can say here, if you want to know about the vector space, what you can do, you just consider a ball, and then you keep on increasing the radius. So when r tends to infinity, this ball covers all the points. I mean, roughly I'm saying this ball covers all the points in the vector space. So therefore, if whatever you say about this ball, this justifies many things about the vector space. And why in particular you can take a unit ball? Because if you have any ball of any radius, then you can always shift that ball, or you can always translate the points in that ball to a unit ball by just dividing every vector by its norm. Then it would be translated to vectors in the unit ball, and therefore you can just focus on the unit ball, and you can say you can just study the unit ball. So that's why, therefore, you can say that unit ball is a geometric summary of a norm. Why this is? Because of this. So why this is true? This is because of the homogeneity, the third property of a norm. Because of the homogeneity, we can do this. So, for example, there are for some standard norms, there is you can draw the unit balls. For example, for LP norms, you can draw. So for LP norms, so if suppose you look at in so you can draw it, let's say in R2, you can draw it, but almost similar shape it has if you draw for like for different P's. So for example, when you talk about 2 norm, then the 2 norm would be, so if suppose we take these, then 2 norm is just this, is this region. This is the 2 norm. This is the unit ball. This is the unit ball with respect to L2 norm. Now, if you look at L1 norm, then so from here you can see that the 2 norm is continuously differentiable. Now, as I was saying earlier, why this is true, from some idea you can make from this ball also. You can see that the surface is very smooth. So this is continuously differentiable. For L1 norm, the unit ball would be of this shape. This would be the unit ball for L1 norm. And for L1 norm, I mentioned that it is differentiable on a smaller set. So that you can see here. And for infinity norm, it would be sort of this. So this norm here, this ball here, this would be the ball with respect to infinity norm. Now, if you take any p greater than 1, then that also defines a norm, and we can talk about its its unit ball. So what would be the shape? So for any p greater than equal to 1, for example, it would be of this. It would be outside unit ball of 1 norm. Okay, this is when, let's say, p equal to say 1.5 or so, and when it is p is large, let's say p is 9, 10, and so on, then the unit ball would be of this shape, close to infinity. So this is when p is, let's say, 10 or so. Okay. But when so I also mentioned in the previous class that when p is less than 1, greater than 0, then that function, whatever function we had defined, what was that function? This was the function. This is not a norm. This doesn't define a norm because it doesn't satisfy triangle inequality. So you can verify that this doesn't define a norm. And one reason is, and if suppose for this function you want to draw all the points in this set, you can still define this set for this function. Although it's not a norm, but you can talk about this ball with respect to that function. So that would be of this shape, like so if p is less than 1, then it would be of this shape. So this is when p is less than 1. So this is not a norm. Now, by looking at the ball itself, you can say whether it is coming from a norm or not. So a few properties I can mention for a ball that you can observe easily. So if suppose we have a norm, so let us start by a norm. So if suppose, so let us make some observation. So if suppose we have a vector space, and suppose that this is a vector norm. So for some norm, I have already like you can draw the norm and you can see this. But whatever I'm saying, that is true for any vector norm on a vector space now. And you can take this, you can make at least you can make some idea by looking at the norm, by looking at the unit balls with respect to LP norm on Fn. So if suppose we have a vector space and this is a vector norm, this is a vector norm on V, then what you can say that this origin, by definition, this origin origin is always an interior point. It is always inside the interior point of the unit wall, right? This you can also prove by using the homogeneity, the third property of a norm. So if you have any norm, then you can define its unit ball, and then you can show that 0 is always an interior point. Okay. Why this is true? Because you can take, let's say, this is very easy, because you can take you can take a ball of radius half, and this is always contained in the unit ball. So it is an interior point. It's very easy to see. Not only this, you can show that unit ball of a vector norm is equilibrated. Equilibrated means, so what I'm saying is that the unit ball of a vector space is equilibrated. What does it mean? It means that if I take any vector x in the unit ball, then alpha x is also an element of the ball whenever, or for all alpha, such that mod alpha is equal to 1. So if I take x, and this is also true because of the homogeneity, right? So if I take any vector x in the unit ball, then alpha x is always there in the unit ball, provided mod of alpha is equal to 1. This again follows because of the homogeneity. Third one is, at least you can see these things in the balls I have drawn here. You can see these two properties are very easy to check, at least for LP norms. Similarly, not only this, unit ball is always compact. So if we are talking about finite dimension vector space only, so unit ball on a finite dimension vector space is always compact. Why this is true? Here, in order to show this compactness, so you have to show that the ball is closed and bounded. So the boundedness follows because of the homogeneity. The unit ball is always bounded, and the closeness follows because of the continuity. So norm is a continuous function. Using that fact, you can show that it's closed. So unit ball on a finite dimension vector space is compact. This also you can show using the homogeneity and the continuity of norm by showing that it is a closed and unit ball is a closed and bounded set. And also you can see that unit ball is convex. So if we have a norm and then we are talking about its in unit ball, then it is always convex. Now you can see here, at least for LP norm, all these norms, when p is greater than equal to 1, these norms satisfy these 4 properties. But when p is less than equal to 1, or p is strictly less than 1, then this set here, this unit ball has this form, so it doesn't satisfy the the convexity. So this set is not convex, and therefore also it doesn't define a norm. Now the question is, these are necessary things. Like if we have a vector space and if we have a norm, then we can talk about it unit ball, and then unit ball satisfy these 4 properties. Now the converse is now the question is whether the converse is true. So if suppose, so the question is, if suppose we have that, so that would be the converse. So can you tell me what would be the converse of this? So whatever I have written in this observation, what would be the converse of that? So what I have written so far is that if suppose we have a vector space, and if we have a vector norm on this, then the vector norm satisfy these 4 properties. So what would be the converse? So the question is the converse true? But before that, you have to show, or you have to say, tell me what would be the converse of this. Can you tell me what would be the converse? What would be the converse statement? Just tell me the statement. Statement of this observation. Anyone wants to try here? Just state the converse.
Like
Just
if
try.
some function
You may be
satisfy
wrong, but
these four properties, then whether that function is a vector norm or not. Basically, some function from vector space to field.
no. Again. So here we are talking about unit ball. So you understand. So this observation is that if we have a vector space and if we have a norm,
Okay, so
then the
some
unit ball with respect to this norm satisfy these four things.
if some set satisfy these properties, then whether that set is unit ball or not, that particular norm.
Right. So not particular norm, but you have to like the statement would be if suppose you have a set, you have a subset that satisfy these four properties, then whether that set is a unit ball with respect to some vector norm only. That would be the converse statement. So in fact, that is also true. So I have already talked about the if part, but the only if part is also true. So I'll write this as an if and only, and I'll leave the proof as an exercise. You can see any textbook. So that is not important. I just wanted to tell you that unit norm, what unit ball satisfies with when you are talking about ball and with respect to some norm. So if we have a subset B of V, it's a subset, okay? Then this set B is a unit ball of a vector norm V if and only if B is first, it is compact with respect to this norm, second convex, third it is equilibrated, and the fourth one is it has 0 as an interior point. Okay. So this is result is if and only if, and the proof I'm leaving as an exercise. All right. So far we have talked about vector norms only. So we still got some time, 10 minutes, so I can at least define what is a matrix norm. So at the beginning I mentioned that first we will talk about vector norm and then we will talk about matrix norm. Now before I define what do I mean by matrix norm, so before I define matrix norm, you can make this observation that if suppose V is the, so I'm talking about finite dimension vector space. So whatever I have mentioned so far in the last two lectures, I have talked about vector norms only. But since the set of matrices is a finite dimension vector space, right? So if suppose the set of n cross m matrices, that can be treated as a vector space of dimension nm. So it is a finite dimension vector space. In fact, you can treat that space of matrices as f nm. So if V is the space of n cross m matrices, then you know that this space is isomorphic to f and m. And we already know norms on this vector norms on this vector space. We have already studied that. Then why to talk why to define a different norm, or why to introduce a new term? The reason behind is that, well, on set of matrices, it's not just a high dimensional vector space. It has a natural multiplication defined on it. So we cannot multiply two vectors. I mean, of course, we can multiply in other sense, like a scalar product, inner product we can take. But in general, we cannot multiply two vectors. But we have a multiplication defined on the space of matrices. That is the usual multiplication. So if we take any two matrices, then there is a way to, like for example, when m equal to n, then we can multiply any two matrices. So there is a multiplication, natural multiplication defined on it, and therefore the natural thing is to relate the size of the product AB to the sizes of A and B, right? By keeping this in mind, now I will add one more property to the norm to make it a matrix norm. So that property relates the size of the product with the sizes of individual matrices. Okay, so that is the main reason to introduce one more term here, which I am calling as matrix norm. So what is a matrix norm? So a function. So here I will, since I want to have multiplication defined on it, I will assume that I will assume only the square matrices here, but there is a way to define like a norm or matrix norm by some other sense on rectangular matrices also when n is not equal to m. But to keep things simple here, notation simplified, I will assume that n is equal to m. So most of the things would be very clear from this. Whatever we want to say on matrix norm, these things will be easy to understand when we keep ourselves in the space of square matrices. So a function, so like we have defined for vector norm. Vector norm is a function from space from vector space to R. Now I'm talking about matrix norm. So the vector space would be space of matrices. In particular, I will consider only n cross n matrices over F. So a function, this function from n cross n matrices. This you can take from F to R, where F is either R or C. This is a matrix norm, or this is called a matrix norm if for all AB, for all matrices A and B, and for all scalars alpha, these are satisfied. These 5 properties. The first 4 properties are the same as in a vector norm. So what was the first one? The function value of A is always greater than equal to 0. So this is non-negativity. This is 0 if and if A itself is 0. A matrix is 0 means all the entries of A are 0. So this is positivity. Then this is homogeneity. And the fourth one is the triangle inequality. So you can see that these 4 properties are exactly same as in a vector norm. But then since the multiplication is defined on space of matrices, we want to relate the size of the product with the sizes of individual matrices. So this property is called as submultiplicativity. So length or function value of the product AB is less than equal to product of the individual values. So this property is called submultiplicativity. So if a function on space of matrices satisfies only these 4 properties, then this function would be a vector norm. But if in addition to that, if it also satisfies the 5th one, then that function would be a matrix norm. Matrix norm on space of matrices. Okay. So I still got a few minutes. So I'll make some observation just from the definition, and then in the next class we will look at some examples. So you can make some observations here. Just by that follows by definition. So if suppose we have suppose that if we have a matrix norm, suppose this is a matrix norm. So when I'm saying matrix norm, so you assume that the underlying space is the space of matrices. Okay. Then clearly, if you look at the matrix norm of A square, what it would be? It is just you can write it in this way, A square, the product, but then because of the sum multiplicativity, it is less than equal to this one. So you can say that for any A, the matrix norm of A square is always less than equal to square of matrix norm of A. This is the first thing, which very straightforward. In fact, in order to prove that, this is true for any matrix norm. In order to prove that a function is not a matrix norm, if you can check that this property is not satisfied, then you can immediately conclude that that function is not a matrix norm. So these properties are satisfied. These are necessary things. So if you want to say something is not a matrix norm, then you can use this property. Okay. Similarly, if suppose we have a matrix A whose square is equal to A, there are such matrices. So A square is equal to A. Then because of the above property, because of the first observation here, you can conclude that length or size of A or norm of A is always greater than equal to 1. Or in particular, if we are talking about a matrix norm, then the matrix norm of identity matrix is always greater than equal to 1. Similarly, if A is invertible, then matrix norm of A inverse is always greater than equal to 1 by matrix norm of A. Why this is? Because A is invertible, so we can use this thing. Okay. So with this, I will stop here. In the next class, we will do some examples. So if you have any doubt, you can ask. If there is any doubt, you can ask, or we stop here, and I'll see you in the next class on Thursday.
So in the second observation, we have to take matrix A to be like non-zero.
Second
Yeah, in the
observation.
second observation.
Yes. Of course. If A is 0, then it is always 0 by the second property. It would be a contradiction to second property otherwise.
Yes, sir.
Yeah, you're right. Any other question here or doubt, query, anything? Okay, if no, then we can stop here, and I'll see you in the next class on Thursday.
So norm of identity matrix will be equal to 1 for every norm, every matrix norm.
For every?
For every matrix norm, the norm of identity matrix will be equal to 1.
For every matrix norm, that you need to show. So from here, so far whatever I have written, we just have this. So now I ask you one question. This is an exercise for you. You just find a matrix norm for which question is whether you can find a matrix norm for which the matrix norm of identity matrix is less than 1. So this is the question.
Okay.
So far whatever observation we made here, from there we can say that it is greater than equal to. In order to say that it is equal to 1 for all matrix norm, it's a very strong statement. So that I cannot say without proof. So, and if you are also saying, then you need to give some justification why this is true. Why by definition the other side inequality should also be true.
Okay, sir.
Yeah. It's a very strong statement that for every matrix norm, identity matrix has a norm equal to 1. That is a very strong statement, and we need a justification or a counter example. So you think about it. I will also think, and then we can discuss in the next class.
Okay. Hello. Hello.